this I've titled part 1 because I'm only going to do part 1 today, but there are actually 2 parts of this. And I went ahead and put the slides in the folder. Oh, did we ever solve? I said I was going to look into that and I didn't. We'll get it figured out. And worst case scenario, I'll email Laura a new link and you guys can send it around. Or email me and I'll just send it to you directly. But I'm surprised that doesn't work. Anyway, so what I'm going to talk about for the next hour is power and sample size, what I call it part 1, the basics. This assumes that you don't really know anything about power and power calculations. Part 2 is simulation methods, just so you know what's in there. So what I'm going to show you is all the pencil and paper kind of stuff and how to use Stata to calculate power and sample size for fairly basic things. When you get into more sophisticated modeling, like multi-level modeling, longitudinal modeling, structural equation modeling, those sorts of things, there are no closed form solutions for those. You can't just plug in a number into a formula and calculate the sample size. You generally have to do that using simulation methods. That has come up enough times that I finally put together a part 2 talk that shows you how to do that. So the second part of this that's in that folder, it actually shows you, it's very dense, it shows you the basics of how to write a Stata program, because you've got to learn how to do that, how to use Stata simulate command to do simulations, how to create artificial multi-level data and things like that. So it's an extension of this, and if you're interested in learning how to do that, I did go ahead and put the slides in there. I'm not going to talk about them, but you'll have access to them. So what we're going to talk about today are basically 3 things. I want to first review the power and sample size concepts, just so for those of you who've never done this before. And then I want to show you how to do power and sample size calculations using Stata. In Stata 13 or 14, we completely overhauled our power and sample size calculators. We've had them in Stata for a long time, but we made them much more sophisticated and a more complete collection of them in Stata 13, and we keep adding to them. And then lastly, I want to show you some strategies to increase power. Because a lot of times you do your first calculation and you think, oops, I don't think I can afford to draw that many samples, or I can't get access to that many people, or whatever. And so you need to figure out a way to maybe increase your power or decrease your sample size, and we'll talk about some strategies for doing that. I put this cartoon in just to emphasize why we even might want to do power calculations. You know, if you just go collect a sample of 10 or 20 people and you do this over and over, you get these sort of random results. Today, coffee is harmful. Tomorrow, coffee is helpful. And so it's a good idea to do power sample size calculations to make sure that you have adequate power, or give yourself a good probability of finding an effect given that it's there, or maybe not doing a study because you're not going to have a good definitive result anyway. So I prefer to show things by example rather than just showing a bunch of formulas. So I've set up this sort of fake scenario, and it's completely fake. I yanked these numbers out of thin air. I was too lazy to even look up something real. But here's the question. So let's say in 1970 the average systolic blood pressure, SPP, in the United States was 100 millimeters of mercury. I'm a biostatistician. All of our examples involve blood pressure, cholesterol. Sorry. Anyway, so due to the increased prevalence of obesity, which goes with, is associated with higher SPP, we believe that the systolic blood pressure in 2019 is 110 millimeters of mercury. So the question we're interested in is, how can we tell if the average SPP in 2019 is 100 or 110? And how many people are we going to need to measure to answer this question with any degree of, I hate to use the word certainty, but any degree of certainty? All right, so the first thing that we need to do if we're going to do a power calculation or sample size calculation is write down our null and alternative hypotheses. So I'm sure you're familiar with these terms, but we need to be a little bit careful about how we write these things down. We need to write down our null hypothesis carefully. So informally, I'm going to state that my null hypothesis is that the average SPP in the population in 2019 is 100 millimeters of mercury. The alternative hypothesis is that the average SPP in the population in 2019 is 110 millimeters of mercury. That's kind of an informal way of stating this, but more formally, I want to add some other features. So here I would state the null hypothesis as the average SPP in the population in 2019 has a normal distribution, specifying the distribution of this thing, with a mean of 100, and a standard deviation of 10. That's much more specific than I had before. The last one was a little more informal. The alternative, I'm also going to be more specific. The average SVP in the population in 2019 has a normal distribution with mean 110 and standard deviation equal to 10. So I've just added a bit of specificity to this. To make the math a little easier, let's center and scale this. So I'm going to subtract off, under the null hypothesis, I'm going to subtract off the mean under the null and divide by the standard deviation. So that under the null, I'm saying that the mean is equal to 0. And under the alternative, again, I'm going to subtract off the mean and divide by the standard deviation. So I'm going to say my mean under the alternative is 1. So I'm comparing a mean of 0 versus a mean of 1. So that's my null and alternative hypotheses. So let's draw a picture here of the mean, or of the distribution under our null hypothesis. So I believe it's normally distributed with a mean of 1, a mean of 0 and a standard deviation of 1. And I'm going to call this axis the z-axis because I'm going to want to use a z-test for my test. At some point I'm going to have to set up a test for my null versus my alternative. So the test statistic I'm going to use is a z-statistic for now. So the z-statistic, you probably remember this from long ago in your intro class, is the sample mean minus the mean under the null divided by the standard deviation, which is then divided by the square root of n, the bottom denominator being the standard error. So I'm going to estimate the sample mean from my data. The 0 is the mean under the null. I know that from my null hypothesis. The standard deviation I'm going to assume is known. I'm going to assume it's 1. But I don't know n. How do I choose n? I need to come up with a value for n for my z-statistic. So I could just go out and grab a convenient sample of 10 or 20 people, but is that really enough? So here's some more definitions. So I'm going to calculate this z-test. And when I'm done, I'm going to need to determine how large of a z-test is statistically significant, right? So what I'm going to do is specify a critical value. I'm going to select a point along the z-axis that I'm going to call my critical value. And if the value of z falls to the right of that critical value, I'm going to say that I reject the null. If z falls to the left of that critical value, I'm going to say we don't reject the null. Again, I'm assuming a one-sided test to make this easy for now. All right, so that's what that critical value is. It's just a point on the z-axis where that's my dividing line between reject or don't reject. Now the probability to the right, under the probability, assuming the null hypothesis in this distribution, the probability under that curve to the right of the critical value is called the alpha level. And I choose that in advance. I choose my critical value so that the probability under that curve is a certain value. And we often use 0.05 as a traditional value for alpha. So that probability under this curve here, that's my alpha level to the right of the critical value. So alpha is defined as the probability that z, my z-test, is greater than that critical value given that the null hypothesis is true. Because I've drawn this distribution assuming the mean, assuming the null hypothesis. Now, what happens if I draw my distribution assuming that the alternative hypothesis is true? Now remember, I assume the standard deviation is the same, but the mean is 1. So this green, the colors are really strange here. This green distribution is the distribution under assuming the alternative is true. So if I look at that critical value, that's the same critical value I had before. Now I can ask the question, what's the probability of the area under that curve, assuming that the alternative hypothesis is true? That's what that green shaded area is here. That green shaded area is what we're going to call statistical power. Again, if the test statistic falls to the right, we're going to reject a null. If it falls to the left, we don't reject. But if we assume that the alternative hypothesis is true, that area under the curve, or that probability, is what we call statistical power. So power is defined as the probability that our z-statistic is greater than that critical value, assuming that the alternative hypothesis is true. Does that make sense? It's the same probability, but we're changing the condition. The alpha level is assuming, in fact, back over here, that little part there is the alpha level, the green part is power. Actually, that entire green part is the power. So it's the same probability, but alpha assumes that the null is true, power assumes that the alternative is true. And I've stated that really clearly here on this slide. Okay? Same probability, but alpha assumes the null is true, power assumes that the alternative is true. Any questions about that so far? Okay. So the other thing I can look at is the difference between these two means. And that difference between those means is one kind of what's called an effect size. There are other effect sizes like odds ratios and things like that. But for our purposes here, we're going to define the effect size as the difference between the two means, and it's often denoted by delta. Now, there are two kinds of effect sizes, and you need to be aware of this using any statistical software to calculate power, whether it's Stata or PASS or Inquiry or any of these. You need to pay attention and read the manual for when they ask you for the effect size, are they asking for the scaled or the unscaled effect size? The unscaled is just delta is the difference between the two means. Scaled means it's the difference between the two means divided by the standard deviation. And if you get those mixed up, you'll get quite different results. Within Stata, sometimes we ask you for a scaled mean, sometimes we ask you for an unscaled, scaled or unscaled. So it's different for different calculators in Stata. And in other software too, I've only used PASS. I've never really spent much time with Inquiry, but years ago I used PASS. And it's the same thing. Sometimes it asks you for a scaled effect size, sometimes it asks for unscaled. So be sure to read the manual to make sure you know which one to use when you're putting that in. Okay, so to solve for sample size, let's say that we're interested in calculating what sample size do we need. We need to specify some things in advance before we can do the calculation. We're going to have to specify an alpha level, and in particular, not only do we need the level, but we need to decide whether we're going to use a one-sided alpha level or a two-sided alpha level. Now, there's kind of a tradition, and there are good arguments as to why we tend to use two-sided p-value or two-sided alpha levels. In the world of clinical trials, I don't know that this has made it out of the world of clinical trials, there's also a thing called asymmetrical alpha allocation. So you can do a two-sided test, but you don't put the same alpha on both sides. You might put 0.04 on one side and 0.01 on the other. And that's kind of an accepted practice in clinical trials, but I don't know that that's made it out of that world. But two-sided is generally the fallback, and if there's no way the test statistic could fall in one direction, then you might be justified in using one side. But when in doubt, you're safe using a two-sided alpha. Typically, alpha is specified as 0.05 or 0.01, sometimes in between. So typically, alpha of 0.05 is used. The closer you get to life and limb or very large sums of money, people will sometimes use 0.01 instead. Anybody know where 0.05 comes from? Was that derived? Did it come down on some tablets off a mountain? Somebody yank it out of a stone, the crown? Where does 0.05 come from? Anybody know? Other than Phil.
It's the square alters a long tail.
It's what? I'm sorry?
Yeah, it's the square.
It is. It's the probability under that curve. But why don't we use 0.1 or 0.06 or 0.49? Why 0.05? So years ago, I had a student ask me this. I went back when I was full-time professor at A&M, and I was embarrassed that I didn't have an answer for that question. So I went back to my office and started looking. I couldn't find it. Finally, I found a little story somewhere on the internet, and I had a copy of the book, so I looked it up. That 0.05 comes from a textbook called Statistical Methods for Research Workers, written by a guy named R.A. Fisher, Ronald Fisher. You've probably heard that name somewhere before. And this was a very popular book in the early 1900s that applied researchers would use as a reference, and they'd use it as a textbook, And in that book, in one of the examples, he says, and if we're willing to be wrong one time out of 20, then we would do blah, 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 blah. Well, one time out of 20 is 0.05, and somehow that 0.05 just stuck forever. And forevermore, we've used 0.05 because it came out of that textbook. But people who have gone back and traced this attribute that 0.05, the fact that we use that now, to that example from that book by R.A. Fisher. It's called Statistical Methods for Research Workers. That's where it comes from. It's just a tradition, and that's it. There's nothing sacred about 0.05, but we treat it that way sometimes. Anyway, the other thing we're going to have to specify is power. If we want to calculate sample size, we're going to have to specify power. Well, where does that come from? Well, that's typically dictated either by traditions in your field of science or by the funding agency if you're writing a grant. So a lot of funding agencies will require at least 80% power. So loosely what that means is that you need at least an 80% chance of detecting an effect if it really is there. Assuming that the alternative is true, assuming that there really is this effect you think you're going to look for, you have at least an 80% chance. A sample size is large enough to give you an 80% chance of detecting it. 80% is used for a lot of things. Sometimes with very expensive large-scale clinical trials, you'll see 90% power required. But anyway, 80% is typical. So two-sided 0.05 alpha is typical, 80% power is typical. Now the effect size and the variance, you can get really stuck on these because you have to either go do some pilot studies or go through the literature or give some serious thought as to what difference between the means seems reasonable to you. And you need to be able to, if you're writing a grant proposal, you need to be able to defend this in some fashion. Where did you come up with that effect size? I have a new drug and I think it lowers blood pressure by 20 points. Well, why do you think that? You have pilot data? Did you use some animal studies? Where did you get 10 from or 20? So you need to be able to defend that effect size, how you came up with it. And then sometimes the even harder thing is the variance. You're going to need some estimate of the variability under the null hypothesis. So where are you going to get that from? Again, you're going to either need some pilot data or you're going to need some previous studies from literature. But you need to come up with some defensible estimate of the variance to use in your power calculation. And just as a strategy thing, I've written, I don't know how many grant proposals in my life. The better you can defend these things, the better luck you will have with writing your grants. If you just make up numbers out of thin air, grant reviewers generally don't like that. They want to know, why did you pick these numbers? Because those are the numbers that then dictate the sample size that you chose. Okay, so let's say that we assume that the null hypothesis, the mean under the null is 0, like we said before, the mean under the alternative is 1. Well, let's say the known variance is 1. We're going to choose a one-sided alpha of 0.05 to make the math easy. We're going to choose power of 80% or 0.80, and our effect size we're going to choose as 1 because the difference between the mean under the null and the mean under the alternative is 1. The difference between them is 1. So these are all of our assumptions. So this is the little formula for doing a basic power calculation, sample size calculation like this. So n is equal to z1 minus alpha minus z beta divided by the effect size, and we're going to square that, and that gives us the sample size. Now where do these things come from and why are they here? So I thought I would go ahead and show you on a graph where these numbers come from that we plug in. So z1 minus alpha, that's this 1.64, that's our critical value that dictates that 0.05 on the right tail. The minus 0.84, that's what's the z-score over here that gives us our power from here. Our effect size is the difference between the two means, so that's where we get these three numbers from. So if we plug in 1.64 minus 0.084 minus 0.84 divided by 1 and square that, we get 6.1504. Now here's the problem. We can't have 6.1504 people without a chainsaw. And so by default in our statistical software, I think most of them do this, and we do this in Stata, we automatically bump any number up to the next integer. So if you run this through Stata, and you'll see this in a minute, if you plug in those numbers, it's not going to tell you 6.1504. It's going to tell you 7. If the number goes at all above an integer, it bumps it to the next integer. It's called a ceiling function if you're interested in these function names. So if we do the calculation, this means we need 7 people, not 6. Because if we use 6, we'll have slightly less power than we said we did. So what we'll end up with was actually slightly more power when we bump it up to 7 people. So that's how we would do that just by pencil and paper, and those are some of the ideas. So now how would I do that if I wanted to do this using Stata's power or sample size calculators? There's so many of these that it was easier to order, rather than put them in a menu system, we put them in this little sort of a control panel. So on the left side, you can choose what kind of a thing do I want to do a sample size calculation for correlation, for hazard rate, for means, proportions, regression, survival analysis, whatever. And when you select something over here, it then populates this panel with all of your different choices for the scenario that you would want to calculate power for. So I'm interested in calculating power for a single mean. So I've chosen power 1 mean, and that opens this dialog box here. So when I open the dialog box in the main tab, right here at the top, it says compute, and so I can select what do I want to compute. So for power 1 mean, I want to compute the sample size. So I'm going to give it a bunch of information, and it's going to calculate sample size for me. So I need to input my alpha level. That's what the significance level is. So I'm going to put in 0.05 here. For power, I can specify power, or beta, which is 1 minus power. Anyway, I'm going to specify 0.8 here in this box. You can check this box that's allowed for fractional sample size, but again, it's not very useful. And then the effect size. So I'm going to specify the mean under the null hypothesis is 0. The mean under the alternative hypothesis is 1. Over here, I'm going to specify the standard deviation, which is again 1. Now this little checkbox below that is important, where it says assume a known standard deviation. If I check that box, if you remember, for a known standard deviation, we have a z distribution. But for an unknown mean, if we estimate the mean, we have a t distribution, right? So if I check this box saying assume, assume a known standard deviation, that means that I'm going to use a z distribution for my calculation. If I leave the box unchecked, that says I'm going to assume that I'm estimating the standard deviation, and it will use a t distribution for the calculation. T distributions have slightly fatter tails, and so it will affect the probabilities and your sample size calculation a little bit. Okay, and then below that we have this thing that says finite population correction, and we'll come back to that later. We'll come back to that. And then sides, do we want a one-sided test or a two-sided test? So we're going to do a one-sided test. So once I've specified all this stuff, I can click OK, and the dialog box will create this command. And the command is power one mean, and you tell it the mean under the null, the mean under the alternative, known standard deviation, that's from checking that little box, and I've chosen to do a calculation for a one-sided test. The output reminds me of the things that I put in, and here at the bottom it says estimated sample size n equals 7. Remember I told you, even though the actual number is 6.15, it's going to automatically bump it to 7 for you. Okay? So that's how we could use one of Stata's power calculators to actually do this calculation. Now, what if, for whatever reason, the sample size is already known, or we're constrained in some fashion, and so we already know the sample size, so we need to calculate power. Last time we calculated sample size, but we knew power. This time we're saying we're stuck with our sample size, so how do we calculate power? Well, again, we're going to have to specify some things. We're going to have to specify the alpha level and the sidedness, so maybe we could assume one-sided 0.05 again. Now we're going to tell Stata the sample size. This could be dictated either by logistical or budgetary constraints, but we're going to tell it the sample size that we have. And again, we have to tell Stata the effect size as well as the variance. So if I do this calculation by hand, these are my assumptions. The mean under the null is 0, mean under the alternative is 1, same stuff as before. But my sample size this time is 5. Maybe for some reason I can only afford to or get access to 5 people. So I'm going to specify a sample size of 5. If I do this calculation, this funny little symbol here is for the cumulative normal distribution. So if I plug in the square root of 5 and 1 for my effect size and subtract off z alpha, I get this number, and I can use Stata's normal function to calculate this number here, and what I end up with is 0.7244. So I have power of 0.7244, assuming that all those other things, my alpha level and my sample size and so forth. So that's how I could do it with a pencil and paper, or I could use Stata's power calculator. So here, rather than computing sample size, I'm going to select power. So if I select power, I specify the alpha level, I tell Stata the sample size is 5, the mean under the null is 0, the mean under the alternative is 1, standard deviation still 1, still assuming a known standard deviation, so we're going to do our calculation with a z distribution. Skip over FPC for now, and I have my one-sided test again. So if I click OK, now the command is power one mean 0, 1, and then I've told it the sample size, n5, known standard deviation, and one-sided. And it reiterates my assumptions that I made, and it calculates my power to be 0.7228, just like my hand calculation. But Stata just does it for me. Now there's any questions up to here? I haven't really paused for questions. Okay, so there's one other possible scenario. What happens if I'm stuck with my sample size for whatever reason, and my funding agency says you've got to have at least 80% power or no money for you? So then what do? Well, one thing that I can do is calculate what's called the minimum detectable effect size. I'm stuck with my sample size, I'm stuck with power, but the thing that I can calculate is what's the minimum effect size I can detect given those other constraints. So now I'm going to have to specify, again, the alpha level, and we'll do one-sided 0.05 again. I've got to tell it the sample size, I've got to tell it the power. I don't tell it the effect size because that's what I'm estimating this time. And I have to tell it the variance. So again, I have my assumptions. I can do my calculations by hand if I want to, z1 minus alpha minus z beta and so forth. And if I do it by hand, I get a minimum detectable effect size of 1.11. Or I need a difference between my mean under the null and alternative that difference needs to be at least 1.11 given a sample size of 5 and power of 80%. So how do we do this in Stata? Well, now we go back to this dialog box, and where it says compute, I'm going to select effect size and target mean. So that's why we have this little compute. What do I want to compute? I can compute sample size or power or minimum detectable effect size. So now I'm going to tell it my alpha level is 0.05, power is 0.8, sample size is 0.5. Now I'm just telling it the mean under the null, because I'm going to estimate the effect size. That's what I'm estimating, is the difference between the mean under the null and the mean under the alternative. So I only tell it the mean under the null. Again, the standard deviation is 1. Check the box, so we use a Z distribution. Ignoring FPC again, I'm going to use a one-sided test, but now it asks me for the direction of the effect. Because I'm estimating the effect size, I might be interested in, is the mean under the alternative larger or smaller than the mean under the null? So I'm going to tell it I'm interested in an effect in the upper direction. I think the mean under the alternative is larger than the mean under the null. So when I press OK, now the dialog box creates the command power1 mean. I only tell it the mean under the null, 0, and then the sample size, power, known standard deviation, and one-sided again. So my minimum effect size that I can detect is going to be a delta of 1.1120, which is what we just calculated. So that means the mean under the alternative needs to be 1.11. Now the reason these are equal is because I used a mean of 0, so the effect size and the mean under the alternative are the same number. But if the mean under the null was 2, then this delta right here would be 1.11, and the mean under the alternative would be 3.11. They wouldn't be equal. They're just equal because the mean under the null is 0. Okay? So any questions about that? I put a nice little slide here that has all the formulas on here, just on the odd chance that you wanted them all on one slide. But that's the idea of how you would calculate them by hand, and then how you could use Stata to estimate these things for you. Any questions? Okay, how are we doing on time? Because we have kind of limited time. All right, so strategies to increase power. Every time I think I've ever done one of these, and I've done a lot of sample size calculations over the years, the answer that I get from the investigator is always, well, you must have made a mistake. There's no way we can get that many people. We don't have enough money to do it. Well, no, you must have made a mistake. You need to check your results. Well, it's usually not that. The problem is that people usually overestimate or underestimate how many people they need. So when this happens, you may need to adjust the assumptions of your model. So here are some strategies that you can use to increase statistical power. And I'll go through each one. One is to increase the effect size. Another is to increase the sample size. And then the last one requires some explanation, and we'll go through that in a moment. So you can use survey sampling methods. So, where'd it go? So one way that you can increase power or decrease your sample size, or well, increase your power, is to increase your sample size. Wait a minute, something's wrong here. First one, yes, here, is to increase the effect size. So remember, the effect size is the difference between the mean under the null and the mean under the alternative. So if the means are close together, notice the power isn't that high. That critical value is staying the same, but the farther apart these two means get, the larger the effect size. That green area is getting larger and larger. The power is getting higher and higher. Well, that's fine as long as you don't get carried away with this, because if I say that I have some new drug that lowers systolic blood pressure by 60 points, first off, that's unrealistic. Second off, that might kill people if they took it. So you need to be careful and choose something here that's actually realistic. You can increase it some, just don't get carried away. Now, another thing that you might do to increase power is increase the sample size. So remember the denominator, and I need to put that in here with the animation. Remember, as the sample size is in the standard error in the denominator. So as the sample size gets larger, the standard error gets smaller. As the standard error gets smaller, the z statistic gets larger, which moves it further out here on the z-axis. And so if that denominator is shrinking, if the sample size gets bigger, these two distributions get narrower and narrower. That increases the power as well. Okay, given all the other assumptions, just increasing the sample size will increase the power. Now, that's not always feasible. You may not have enough funding or access to that many people. And you can't get too carried away with this, because if you say, oh, I need 20,000 people to do this study, you're not likely to get funded there either. So it's a strategy, but it has to be used wisely. Sometimes you can combine these two. You can shift the effect sizes apart, increase the effect size a bit and decrease the sample size a bit, and some combination of those two may get you where you need to go as well. So those are two relatively simple ways of increasing statistical power. Now, there's a third way, and this is not always worth the trouble, but if you've never seen it, has anyone taken survey sampling, a course in survey sampling? Not really? Okay, so this is like a really quick version of survey sampling of what this is. So we're going to talk about some new concepts. Probability versus non-probability sampling. You probably talked about that long ago in intro stat. Sampling with and without replacement. That you probably will jog your memory too. And we're going to use these things to calculate something called the finite population correction factor, or FPC. So, back to Stat 101. Probability sampling refers to the idea that we can actually compute the probability that any particular person or element is selected into our sample. If we can't do that, then what we have is a non-probability sample. And what most of us have done in our careers and we've learned about is non-probability sampling. You don't actually know, or you can't calculate the probability that any particular person or element ends up in your sample. But there are some situations where you can. So let's imagine that you have some target population. You're interested in doing a study and you want to infer something about the population. And that's why you draw a sample, because you can't sample everyone, you can't measure everyone, so you draw a sample and then you want to draw inferences back to the population. So let's say that you have some imaginary population, we're going to call that the target population, that you want to infer your results back to. But you can't enumerate everyone in the entire population, but you can get something that we're going to call a sampling frame. So a sampling frame is essentially a list of all the possible people or objects that could end up in your sample. One nice example is if you were talking about a city. In the old days we had these paper things called phone books, and they were lists of people's names and their phone numbers. You guys have probably never seen these things, but they used to exist. They were called phone books. Well, a phone book might be a nice sampling frame. If you were interested in learning something about a town or a city, you could take the phone book, which has theoretically almost everyone, not everyone in the population, but most people. That might be a good sampling frame, and you could come up with the same way of sampling from that sampling frame where you just go through, start in a random spot and maybe go through and sample every 100th person or something out of the phone book. So the sampling frame would be the phone book, and the total number of people in the phone book is big N. So let's say that you have a town of 30,000 people, so there are 30,000 people in my sampling frame, that's my big N. My sample is the number of people that I draw from that sampling frame, and that's my little n. So the probability of ending up in the sample is then little n divided by big N, right? Because for any one person, if there are 30,000 people in the sampling frame in the phone book, I have a 1 in 30,000 chance of drawing a certain person. But if I'm going to draw n of those, I have a 1 over 30,000 plus another 1 over 30,000, and if I do that n times, the probability that any person gets sampled is n divided by big N, little n divided by big N. So that's the idea of a sampling frame and a sample and drawing a probability sample. I can calculate the probability that any particular person in the sampling frame ends up in my sample. If I don't know that number, the big N, then I have a non-probability sample. So next let's review sampling with and without replacement. So let's say that I have a bucket with 8 balls in it, and 8 of the balls are green and 2 of the balls are red. They kind of look like that on the screen. So in this bucket, I have about a 2 out of 10 chance of drawing a red ball. If I just reach in and draw a random ball, pull out a random ball, the probability of drawing red is about 2 out of 10. Probability of drawing a green ball is 8 out of 10, right? So I take the ball, I pull it out, but then when I'm done, I put the ball back in, and now the probability of drawing a red ball is still 2 out of 10, and the probability of drawing a green ball is still 8 out of 10, because I've sampled with replacement. I took the ball out, but then I put it back in again after I drew the sample, so the probabilities are the same. Now what happens though if I do this without replacement? So I reach in and grab a ball. Well, before I grab a ball, the probability of drawing a red ball is 2 out of 10. I take a red ball out of the bucket, but I don't put it back in. Now the probability of drawing a red ball is 1 out of 9. Because I took one red ball out, the probability changed. The probability of sampling a red ball. Next, let's say I pull a green ball out, If I take a green ball out of the bucket, now the probability of drawing a red ball is 1 out of 8. It changed again. Even though I didn't draw a red ball, I changed the denominator, so the probability changed again. And that's what happens when you sample without replacement. Every time you draw a ball out of the bucket, the probability changes for the remaining balls of the bucket. So the bucket here is our sampling frame, and the balls that I draw out of that are the sample that I draw. And if I'm drawing from a finite bucket or a finite sampling frame without replacement, that means the probability is changing every time I draw someone. So imagine we wanted to draw a sample from this room, just the people in the, I want to draw a sample of 5 people. If I sample you, I'm not going to put you back in and then draw you again because I don't want you twice. I want everyone at most 1 time. So in reality, I'm drawing or sampling without replacement, right? And if I do that, it's changing the probability every time I draw another person. And that's what the finite population correction factor is getting at. I'm sampling from a finite population. And so that's what this FPC is. And the FPC, and we're not going to go dive into all the why of this, but the finite population correction factor corrects for this changing probability, so to speak, or the fact that we've sampled from without replacement from a finite population. So the FPC, the finite population correction, is defined as 1 minus little n over big N. Now I have to know big N, right, and little n. So that's what the FPC is, and the standard deviation corrected for, the standard error, whatever, corrected for the FPC is equal to whatever the standard deviation was before times the square root of 1 minus this, or the square root of the FPC. Well, that means that the FPC, because it's going to be less than 1, is going to shrink the standard error, the standard deviation sum. And if I shrink the standard deviation sum, that will also get me more statistical power. So let's imagine a scenario where I have a study population of 100,000 people, maybe it's a city. And if I draw a sample of size 50 from this sampling frame of 100,000 people, the finite population correction factor, I'm just going to call it FPC, would be 0.9995. So if I ignore the FPC, the standard error might be 0.4472. If I multiply that times 0.9995, it's 0.4471. So I've reduced my standard error sum, but I haven't reduced it by much. And that's because I drew a fairly small sample relative to the population, the sampling frame. But look at what happens as the sample size gets larger for the same sample population size. Once I get up to a sample of 10,000, my FPC is 0.9. And if I multiply the standard error times 0.9, it shrinks it a fair amount. The standard error, ignoring the FPC, is 0.0316. If I take the FPC into account, it's 0.0300. That's still not a big decrease, but it can help you out, especially if you're kind of on the border of if let's say you calculate your power and it's 0.78 and you really can't move, you can't change other things. If you're in a situation where, and there's this rule of thumb that if you are sampling 10% or more of the target population, this can actually help you out. Can be worth the trouble to actually calculate this. Most of us ignore this, most of us don't even know about this, we go on our merry way, but if you're familiar with this and you're in that situation, this can actually help you out. The only time this ever happened to me was a study years ago. I was helping some folks plan of nursing homes in the state of Texas, and I don't remember the numbers exactly now, and we weren't interested in the people per se, in the individuals in the nursing homes. These were characteristics of the nursing homes. And we were only interested in the state of Texas, and you can get a list of them all. And we were sampling more than 10%. I think it was like 15 or 20% of all nursing homes in the state of Texas. So that made it worth the trouble to go through and calculate these FPCs because it got our sample size down a little bit. So I've done this a bazillion times and only run into this situation once, but it can help you out. Now, so that's what this little box right here is in our dialog box where it says finite population correction. That's the sampling rate, and I can type in 0.1 here, and it will take that into account when it does my power calculation. So before it was like 0.72 when I used all the same assumptions. The power was like 0.72. With an FPC of 0.1, power is now 0.76. Well, that didn't get me over 0.8, but let's imagine that you're right on the border. Your power is 0.78. That FPC might be enough to bump you into the 0.8 range. So, now another question you could ask yourself in advance before you go to all this trouble is, rather than putting in a particular number like 0.1 for the FPC, you could put in a range of values for the FPC and just ask yourself the question, if the FPC was 0.05 or 0.1 or 0.15, how much does that affect my power? So what you can actually do here is put in a range of numbers rather than a single number, and Stata will give you a table rather than a single number. So now the command is power 1 means 0 is the mean under the null, 1's the mean under the alternative, sample size is 5, blah, blah, blah. But for my FPC, I put in a range of numbers. I've asked Stata to do the calculation for an FPC of 0.05 to 0.15 in increments of 0.01. And what I see below here is a table, and it shows me my alpha level, my power, and N, and so forth. It's the same for everything here except for FPC. I've deliberately manipulated FPC from 0.05 to 0.15, and Stata's calculated power under each of those sets of assumptions. So here I can see that for FPC of 0.05, power is 0.74, but if FPC is 0.15, my power is 0.78. So if you're thinking about doing this, it might be worth doing this little exercise before you go to all the trouble to find a sampling frame and all that, to ask yourself the question, okay, if my FPC were 0.1, how would that change my calculation? Would that really help me or not? The other thing that this illustrates is the fact that I can put in a range of values for some of these things, like the sample size or the mean under the null and so forth, and Stata will create a table for me. The other thing that the power commands will do is it will create a graph of these results. So in the power 1 mean dialog box, if you look over here, there's a graph option, a graph tab, and I can click on the properties and I can define the graph however I want. So here I have a graph where the horizontal axis is the sampling rate, or the FPC, ranges from 0.05 to 0.15, and the vertical axis here shows me the statistical power, and so I can see what is the effect of the sampling rate on statistical power. So I can see it as a graph instead of as a table. And you can do this for different sample sizes. I might want to do this for sample sizes of 10, and it'll show me one line for sample of 5 and another assuming a sample of 10 or something like that. So you can do nice power curves, some people call them, using these power commands. What I have in the next set of slides in part 2, and we're going to finish actually early, which is good. In the second talk, I show you how to go through and add first off, how to do power by simulation, and then second, how to add your simulations to Stata's suite of power commands. And that allows you to create these tables and graphs without having to write all that code yourself. So that's what's in the slides for the second half of this. There are a bunch of videos. A couple of years ago, I just got carried away recording videos for power and sample size. So on our YouTube channel, there are videos there's a tour that kind of shows you the basics like what I just did here. And then I go through and show you for 1 mean, how do you calculate sample size, power, minimum detectable effect size. For 2 paired means, what if you have a paired t-test sort of a scenario? How do you calculate sample size, power, minimum detectable effect size for 2 paired samples? One-way ANOVA, how do I do it for that? Compare one proportion to a reference value. Compare 2 independent proportions. 2 paired sample proportions from 2 paired samples. So there are tons and tons of videos up on our YouTube channel on how to do power calculations like this. I told you before that the slides are available here, but evidently they're not, or it's not working on this network anyway. So I'll take a look at that here in a moment. And again, as I said earlier, you're welcome to email me, please do. But I'm gone a lot, and so it may take me a while to get back to you if you email me. So, and we're done early because I hear you guys have to go somewhere else in another building, so this worked out well that we finished early. I'm happy to hang around and answer any questions, but other than that, that's what we have. So thanks for coming today. Looks like there's still a little bit of food over there and some water. Thanks. Any questions for the whole group? Okay. Well, I'll hang around here for a bit and answer any individual questions. Thanks again for coming. So you never did get into the email?
No.
Let me try it on my phone over 4G. It's possible there's a typo.
Probably thought we were talking about University of South Carolina.
Yeah, but I create my own tiny URLs, so.
Are you trying to finish up now or?
But I may
Are you trying to get out early or something? No, but you know. So it's all about
consuming.
Now, are you going on that? If you're on all interested in this, in December, another one of these.
That's the way